Dr. Obinwanne Chukwuemeka, from diplomat from the American Academy of Optometry. Please take us away, Doctor.
Good evening, everyone. I'm Obinwanne Chukwuemeka. This research work titled Peripheral Refraction using the simplified peripheral and ciliary refraction component, which would refer to as SPARC, in children and young Nigerian adults. This paper was, or this research work was presented as a poster in the American Academy of Optometry a few weeks ago at Indianapolis. And it's something that's still ongoing, so we're presenting preliminary findings here. Next slide.
You muted, Obi.
Oh, so sorry. Basically, we know that for individuals who have myopia, we refer to peripheral refraction or peripheral hyperopic refraction a lot, because that has dictated or better helped us understand how myopia progresses from an optical standpoint. And clinically, we know that the gold standard for measuring peripheral refraction is using the open field automated refractor. The issue with this is it's quite an expensive instrument. It's something that's not widely available, and something that the average, would I say, African practitioner may not be able to afford. Yet we sometimes blindly prescribe myopia management strategies that work based on the principle of peripheral hyperopic defocus, without actually knowing whether peripheral hyperopic defocus is contributing to that patient's myopia progression or not. So to bridge this gap, the myopia lab at LV Prasad Eye Institute, headed by Dr. Pavan, who's also a co-author on this work, looked at a way to bridge that gap and bring this closer home. Now, we are all used to using the peripheral, we are all used to using retinoscopes. We're all used to using a trial frame while conducting refraction. So what was done was to create a simplified method to measure peripheral refraction that can clinically tell the clinician that this patient has peripheral hyperopia or peripheral myopia that may be contributing to myopia progression, and institute the appropriate strategy. So what was done was to develop a trial frame-based device. It has a filter. From the image there, figure 2, you can see something mounted on the trial frame. That has something called a radium filter at the center. And while performing retinoscopy, that filter guides you to know whether you're performing on central retina, that's 0 degrees, or whether you're 22 degrees nasal or 22 degrees temporal. Now, the results from this device was compared to the open field automated refractor, which is considered the gold standard. And the results were, the agreement was quite remarkable. So what it means is you can actually use the peripheral, the SPARC device to measure peripheral refraction clinically and still get the same results as you will get with an open field automated refractor. Now, this was done in an Indian population, and the findings were published in the Translational Vision Science journal. So to bring this home to the African population, that's where this peripheral refraction group was formed. And what we had done was over 3 centers that are focused on myopia management. We had recruited children and young adults who had presented for eye examinations, who met our inclusion criteria. We had performed normal cycloplegic refraction, performed peripheral refraction under cycloplegia using the SPARC device as well, measured their axial length using an ultrasound biometer, and based on the data that we had collected, these were analyzed using ANOVA because we were looking at the peripheral refraction in different retinal eccentricities, and also looking at their axial length. What we found was that for individuals who had myopia, we found a significant relative peripheral hyperopic defocus, which was more nasally compared to the temporal region. So there was an asymmetry in the peripheral refraction that we found. In individuals who were not myopic, we found relative myopic defocus. And there was some asymmetry, but the asymmetry was more in individuals with myopic refractive error compared to those without myopic refractive error. As would be expected, the axial length was longer in individuals who had myopia compared to the non-myopes. And yeah, basically that was what we found. In conclusion, again, this study for now is being done in Nigerian children and adults. Like I said, it's still ongoing. But in conclusion, we can use the retinoscope to measure peripheral refraction using the SPAC device clinically and obtain large-scale data for a normative database for children and young adults of African descent to actually map out the type of peripheral refraction that we have, because we know that there are reports of racial differences in peripheral refraction. So what that means is clinically, the implication of that would be some of the strategies that we use for myopia management may be better suited to a certain race or may not be best suited for a certain race based on the peripheral refraction. The graph there just basically shows what I've already talked about. For the myopes, it's represented in black, and for the hyperopes, it's represented, or the non-myopes rather, it's represented in red. You see that it sort of mimics what we would expect the retinal shape to look like. Basically, what it means is centrally in the myopic retina, it's more pronate, pushed backwards, and in the periphery, it's more forward, creating the peripheral hyperopic defocus. And we tend to see that the way the graph moves at the extreme shows that there is some asymmetry to the peripheral refraction that we reported. The members of our research team, Damian Ichendu, Sheridan, Justin, Chinemema, Ohanyiri, Swapnil, and Pavan from the myopia lab at LV Prasad, and Professor Kovin Naidu. Thank you very much.
Thank you, Doctor, for your presentation on myopia. We now have 2 minutes to ask the doctor any questions about his research.
Could I ask a question? Hi. Hello, Obi. Great to see you here. This is Tuti Misra, Associate Professor in University of Auckland, New Zealand, and editorial board member at Scientific Reports. It's a great research, Obi. Well done. It's very interesting. An excellent graph. The mimicking of myopes and non-myopes, that was very obvious. One question I have in a clinical setting, would you use this device in each and every patient, or would you concentrate, or would you only do it if you are planning a specialized myopia treatment, or maybe if you're thinking of atropine drops, or if you're thinking of ortho-K, would you consider for those patients or everyone?
Thank you for the question, Shruti. Clinically, I think it could be used for everyone. It could be used for everyone because when you're performing retinoscopy, sometimes we're not sure if we're hitting the central retina or if we're off axis. This device may guide you to perform retinoscopy at the appropriate angle. However, I would say it might be tedious to do this for everyone. So you might want to limit it to individuals who you're planning some form of myopia management strategy on, but I don't see why it can't be used if you decide to maybe guide your clinical retinoscopy. Sure.
How long, sorry if I missed it, how long does it take to use this device? Additionally?
So we haven't actually measured that, and I'm not sure if the myopia lab at LVP, I did that. But from personal experience, it's going to take 3 times the time you would normally perform your usual retinoscopy, because you're going to be measuring centrally, nasal, and temporal. So you're going to repeat the same thing, and then you're going to do that for the right eye and the left eye, and then yeah. So about 3 times the time it will take you to perform normal retinoscopy.
Just a follow-up to that, Obi, if we still have time, Nalova, do we?
We are actually supposed to go on to the next presenter.
Okay, that's fine. Yep, no worries.
Sure. So obviously, Doctor, if you have questions, you can put them in the chat.